All right, we're back at it here. Hope everyone had a good lunch break who's joining us virtually. My name is Mark Mann. I'm one of the engineering managers at Price Industries. My focus is on terminal and fan coil products, so we're going to talk about decoupled cooling systems in the same way, the same type of system design, but just a different approach. And to kind of work through that transition, the first presentation here is going to be actually integrating terminals and chilled beams together. So how does that approach happen? Whether it's two different endpoint terminals providing our sensible cooling to the zone, or whether it's terminals and chilled beams actually in series with one another, and some of the considerations that you might need in design to make that work well. So there's a bunch of topics we're going to go through. I do want to do a bit of a decoupled cooling system recap just to refocus us quickly. I have a bit of a different approach to talk about it, maybe some of the rationale in industry, why we see it done more prevalently. Often this is referring to ASHRAE. That's going to be quick. Then I want to talk about a hybrid approach, terminals in series with chilled beams, how they measure and control airflow in a different way, and how testing and balancing them, especially in series with one another, we need to kind of have some additional considerations. So I'm going to start off with the discussion of traditional VAV versus DOAS. And Ken, this is the one that I think we'll have some fun discussion about it afterwards. But this actually comes from the ASHRAE DOAS Fundamentals Handbook. And I do like to say we're not trying to negative sell any particular type of system. Price is bread and butter. The most of the products that we sell are for mixed VAV air distribution systems. So different approaches work for different applications, although there are some benefits that we see to efficiency with DOAS systems. And ASHRAE makes some claims about VAV systems as well, that they sometimes can have poor humidity control, and that they often can also have unpredictable or poor ventilation performance. Something that I've seen anecdotally, experientially, is that we can also see a risk of overcooling at times for internal zones with these types of systems, which means we have to add a bunch of reheat. It depends on the climate. Here you guys do heating anyways, so it's not so much of a concern, but for some markets, that's a further consideration. And so the way I want to kind of frame poor and unpredictable ventilation performance and what ASHRAE means comes from this example, which is a reworked example with some calculations that maybe just are more applicable to common applications, but it comes from the DOAS Fundamentals Handbook. So we have an open office or an office environment here with our facade at the bottom of the screen, internal zones at the top. It's a bit of a snapshot. We can imagine this as a particular portion of a larger tenant fit out project or something like that. And we have different zones that have different minimum ventilation requirements per ASHRAE 62.1. So this is going to be based off of the ventilation rate per person, the ventilation rate per square foot within the space, and then also how effective we are at actually mixing air into the breathing zone within that occupied zone. So in this case, with an open office, we're looking at 5 CFM per person and 0.06 CFM per square foot as the requirements from ASHRAE. If we were looking at a classroom, that would move up to 10 CFM per student and per teacher per person, mostly students, and 0.18 CFM per square feet. So yes, the built environment cares a lot more about kids than it does about us, and that's okay. In this case as well, assuming mixed overhead air distribution in cooling, our ventilation effectiveness is 1. So that means we're as effectively getting air into the breathing zone as we are into the return. It means we're not seeing too much stratification. It means we're mixing the space effectively so we have the same pollutant concentration throughout the breathing zone. Now, this same system in a VAV system is also going to have to deal with the space cooling load. And that's going to vary obviously with occupancy, solar load, zone envelope. It's going to depend also on other internal loads from the electrical system, from lighting, from equipment that we may have in the space. And this same MBH per zone, it's going to be taken care of by air only. So the airflows I have on screen here are assuming a 55-degree saturated supply temperature for design day, and that's how much CFM we're actually going to need to reach the load of each zone. And where ASHRAE says poor or unpredictable ventilation performance can come from is because we have a variability in the ratio of fresh air for ventilation to supply air for cooling. Now, their claim from a fundamental laid out perspective is this can be a risk of excess outdoor air or overcooling. And that is true, although there's capability to sequence different zones in ways that would reduce that risk. There are ways to optimize the system further. This is very much a cookie cutter design, but it is true. So in this case, the highest ratio of ventilation air to supply air is going to set that ratio for the air handler and for every other zone served by that air handler. Often firms might just have for different applications certain rules of thumb for percentage of ventilation air to supply air. However, if we were going to calculate it out zone by zone, this would be the type of approach you'd be taking to figure out how much ventilation do we actually need to total supply on design day. And with that required ratio, we then can also look at, the required ratio versus the ratio we need. And through that, we'd be able to calculate excess fresh air. So this is under the assumption that we're actually matching that required maximum ratio. Now, it's also possible instead, rather than excess fresh air, if the system was balancing correctly, you could have a lack of fresh air to certain zones. You could have a risk of maybe overcooling internal zones in this case as well. But this is ASHRAE's rationale and where it comes from. And so from their viewpoint, the alternative being 100% outdoor air, that means we're only providing outdoor air to each zone. Therefore, the ventilation of each zone is satisfied regardless of the cooling load. That decoupling of ventilation and latent versus sensible means that we can hit ventilation and latent perfectly on the nose. However, of course, it does beg the question, how are we going to cool the zone instead sensibly? And so the rationale there, we at Price move to hydronic products. Hydronic is what Buckley mostly does in these types of applications as well, as far as the equipment that they can provide. You could potentially see refrigerants, VRF, something like that as well. But from Price Industries, what we can do at this point is use hydronic heating and cooling to handle the thermal comfort of the space. And then we'd use the DOAS terminal system to handle the latent load of the space. And we can also control the entering air conditions of the fresh air to further help with that latent load as well. Any questions on that example? So, yeah.
Ventilation air, one room, and return air flooding. Take credit for that.
Yeah. Absolutely.
So, how does that alter your 0.179? You don't really have to have 179 across the whole system, right?
Absolutely true. So yes, that excess air that we looked at could be returned back to the air handler, recirculated to the space, and that could provide a credit to us for how much ventilation air we need to bring in. So that ends up being like a mass balance type calculation that you perform. And that's something that you can still do in 62.1. So there's feasibility to that. Of course, it also depends on the classifications of air quality you need. So when we look at a school environment that maybe has a cafeteria, which also could have very high air requirements, that can't get mixed back into the space because it's a class 2 type air, whereas class 1 is our occupied spaces like our classrooms. So some air still usually in the system is going to get exhausted out unless it has its own designated air handler. And so there's a lot of different philosophies. What we can do with that excess air, there's further productivity we can add to this outdoor air excess that can be reutilized in the system. There's many approaches that we can do. The ASHRAE DOAS Fundamentals Design Guide Handbook has a paragraph or two that kind of references that, but it doesn't go into detail necessarily all the options on the traditional VAV design at that point, because that's more so covered in 62.1, in 55, and then also just in the ASHRAE Handbook of Fundamentals. But it's a very good point. This isn't necessarily just lost to the environment. And just to close that out, my spiel there for everyone online, the question was, that excess outdoor air, can we not put it back to the return and get a credit for it? And the answer to that, much more briefly, is yes, you can. Okay, so maybe everyone saw my quiz question, and I'd love for everyone online to participate in this as well, but we're gonna survey the room with a show of hands. We talked about the difference in sizing of the way we actually supply and move heat transfer mediums throughout the zone in a DOAS system or throughout the building. But my question here is, how many times greater is the volumetric heat capacity of water in comparison to air? So anyone online, write into the chat A versus B versus C versus D with your guess. For everyone in the room, raise your hand if you think the answer is A, 3.5 times. So how much more energy is water in comparison to air? B for 35. Someone's going to be brave here. C for 350. I'm seeing C. D for 3,500. Andy, why 3,500? Just intuition? I love it. It is D. D is the answer. The rationale here is we have about 1,000 to 1 density from water to air. And then the coefficient of heat performance for water to air is about 3.5 to 1. So we multiply those together, we get the volumetric heat capacity of water in comparison to air, and we get a very impressive number that you can walk into your narrative meetings with owners and say, this is why you use DOAS. But the point here would be, it's a lot easier to move energy through water than it is through air. Any questions on that? So I know Chris referenced this before. And this was actually, Ken, I know you wanted to maybe see where some of this data came from, so we could forward you that resource afterwards as well. But when we look at airside considerations, and I'll be brief with this because it was already discussed in some really good detail, but we're looking at energy savings, smaller ductwork size, smaller mechanical equipment size, which when we look at stretch energy goals locally in Mass, that's really critical and something to consider for new construction, new design. We're seeing lots of great comfort, and in many cases, some reduced maintenance as well. The big rationale here is total sensible latent in ventilation through a traditional VAV system. We're seeing for the air side, partial sensible, so we are getting some sensible cooling because the air is colder than the space set point, but latent in ventilation being the critical requirements of the DOAS air system instead. So my next section here, I want to talk a little bit about estimating ventilation rate and dew point. So when we look at a DOAS system, the fundamental goal of the DOAS system from a zone consideration perspective is that we really would like to provide only the minimum amount of outdoor air required to meet the ventilation rate of the room. Now, we still have to worry about latent loads. We still have to maintain a comfortable humidity within the space. So the gold plating of this type of design from a zone perspective is, let's try to handle the latent load requirements of the zone without increasing that volume further. Of course, we often have to. Sometimes we need that higher volume of dry air to actually offset the latent load of the zone, but ideally, we can do it with the same volume. And I just wanted to talk a little bit about what that process would actually look like from a design perspective. So if we recall, we have our outdoor air required per zone. We already went through this. Each zone has a different minimum ventilation requirement per ASHRAE 62.1 based off of the number of people and the square footage, how well we mix the air within the space, and the type of space that we're actually constructing. Well, we also have different latent load requirements in the same way we had different sensible load requirements for the zone as well. And this is what we need to maintain typically about 50% relative humidity on design day. So that's where that 75-62 dry bulb, wet bulb temperature comes from that we often see kind of assumed within engineering design. That is 75 degrees as a design day temperature with 50-degree relative humidity. And in this case, with it being an office, I didn't actually perform load calculations for all these zones. I just wrote it all out and dreamt it all up. So my assumption in this case is 200 BTUs per hour per person, which is from ASHRAE Handbook of Fundamentals, based off of moderately active office work. I looked at the square footage of each zone, looked at the ASHRAE 62.1 assumption for how many people we're going to have in each zone, and that's how I came up with the latent loads. So we need this much latent cooling provided to each zone on design day. And what we want to do is try to meet that with only the ventilation air requirement. And this equation here on screen, QL equals 0.69 times the ventilation rate times the difference between the humidity ratio of the space and the supply air is what allows us to kind of calculate this out. And so what ends up happening when we go through these kinds of examples in this exercise with an office environment is that it's going to end up needing us to cool the air further on design day than the 55 you'd typically see in an all-air system. Now, there's a few different approaches for this. Of course, we could dehumidify the air with desiccants. We could keep it at an elevated temperature. We could subcool it, reheat it, and deliver it at 55 degrees, not saturated and drier. But what we often see, especially in certain markets that we'll say are more shoulder season most of the time, so like a Seattle market, is that they actually keep this air cooled to a 47-degree saturated supply air temperature instead. They use that as sensible cooling for the space, and on design day, that dries the space out as well. And this is all assuming a maximum desired space dew point of 55. So similar in this exercise, you'd go zone by zone, look at the worst case one, and we would set our supply air temperature from our DOAS air handler to that point, and that's what's going to provide our latent cooling. I apologize for all the math. Any questions on that? I promise we talk a little bit more about product and philosophy and theory moving forward here. Yeah.
Did you check your sensible? Some situations I've seen using that analysis,
yeah, you absolutely could, in some cases, require some reheat on internal zones depending on the market. It's certainly possible. I would say generally when we look at a design day summer condition, which is kind of what I'm assuming and looking at here, we're going to need enough cooling in those internal zones too, that we usually aren't overcooling the space requiring reheat. But analysis would be good to look at depending on the project, and a risk of overcooling is a consideration with DOAS systems at times if you're taking this kind of approach. So the question there was, internal zones, can we overcool them with this type of saturated supply air? You guys heard my answer first. I'll try to do that in reverse next time a question's asked. It's a risk. I don't see it come up too often anecdotally, especially when we look at more temperate climates, but it's something to consider during design. So I want to talk now about hybrid decoupled cooling systems. I'm going to flash a couple slides and go through them briefly just to talk about the product that we haven't had as much of a spotlight on so far, the fan-powered chilled water terminal, aka the fan-power series DOAS box, aka the chilled box. It has too many names. It's very frustrating. ASHRAE calls it the fan-powered chilled water terminal, so that's what I'm going to call it for the rest of the presentation. Now, when we look at this type of product, really my high-level elevator pitch for anybody, and we just talked a lot about chilled beams, it's chilled beam performance with a fan-powered terminal unit layout. So we're still seeing the same primary air volume as chilled beams, the same primary air conditions as chilled beams. We're seeing it work with the same system designs. So when we look at heat recovery chillers, when we look at incorporating air source heat pumps, when we look at condensing boilers, it slots in the same way with the same rationale as a chilled beam system. And we're still looking at that elevated chilled water temperature of 56 or 57 degrees Fahrenheit, which is going to make sure this large coil on the return of the unit stays dry and does not condense. Now, a couple things to note with this product which come up, and I'll be brief with this because we're going to talk about it more in the next presentation. We do have a drip tray. So if this coil were to condense, especially on startup, that would be kind of the most common time we would actually see a system like this condense. We could just catch what dribbles down into the pan. It's not piped, but it would evaporate away over time. So that's a consideration there. The way this equipment actually works is we have our ventilation volume, which is usually about a quarter of supply air volumes that we need for the space. The difference between the fan set point and the ventilation set point for the product is air induced through the coil, sensibly cooled through the coil, mixed with the ventilation air so we can still supply, anywhere from 55 to 60 degree Fahrenheit air into the zone for design day cooling. Any questions on this product? So other high level things, they have a lot of capacity localized into one piece of equipment, up to 36 MBH. They come in a variety of sizes and configurations with a number of different accessories that can help with very large zones and zones that are very variable in their occupancy. So it is a really good exterior component. It's really good for exterior large zones. Of course, it can be utilized throughout a building, but if we look at a DOAS system, typically the larger the zone and the higher the loads, the more we'd maybe pivot towards this product. Now, the case for the hybrid system and using both of these together, so we're going to have the same duct layout, the same core duct layout completely. We're going to have very similar piping. So whether that's a 2-pipe hot-cold changeover or a 4-pipe system, we're going to run the same type of circuitry, the same type of loops. The only difference is maybe some consolidation of equipment with the DOAS box and a few less, endpoints potentially. But when we look at this and the case for kind of putting them together is we get that efficient occupant comfort. We still see very low space maintenance because of the utilization of chilled beams without filters or motors. We're still seeing very low humidity environments. We have the benefits of architectural features and products that can fit behind a ceiling or in a corridor, very uniform heating and cooling. And ideally, this can be very quiet because we can handle larger products for larger zones, smaller products for smaller zones. And so when I look at the comparison of these two products, and I know Matt spoke to this, so this is a bit of a refresher here. From an acoustical perspective, the chilled beam is going to win out when we don't look at a fan that's rotating. Generally, much quieter operation for that, where the fan-powered box is better suited maybe for a larger zone and load. Now, I will say for heating in particular, the DOAS box has a little bit more flexibility, which we'll refer to, but electric coils, very low entering water temperature capable coils, and generally it's an additional coil in a different location, so you don't kind of cut your coil into cooling versus heating. You manage them both separately, which can be an asset. Architecturally, the chilled beam is really viewed as a visual asset by a lot of architects and engineers and building owners. So that can be a huge asset. But in some cases, an owner might want products hidden behind ceilings. I would say generally architecturally driven projects often lean more towards the chilled beam, but the flexibility of a fan-powered terminal, potentially with perimeter slots or cloud or open ceilings. We're seeing a lot of open ceilings with kind of more industrialized looking equipment that gets painted. That's popular. So there's an option there. The chilled beam is generally lower maintenance without its motors and filters, and then variable loads because of this equipment, which can handle up to 36 MBH all the way down to, very low MBHs. That makes it really well positioned for variable occupancy. So two great tools in the tool belt. I like to think of it as a large Phillips head and a small Phillips head screwdriver. Both do the same job. You probably want them both in your tool belt because sometimes you have a little screw to deal with, sometimes you have a big screw to deal with. Sometimes you don't have all the clearance for a long-handled screwdriver, you need just a smaller one. So the same approach, the same outcome, just a different package for it. Any questions on that? Okay. So this is an actual project that I helped the engineer lay out and do some design assistance on. And this is a project in Seattle. It's Google Block 38. This is a built and commissioned building at this point. And the engineer and the architect narratively had gone to Google with the approach, we're doing chilled beams, we're doing a DOAS system, we're using them both together. But they really were struggling with where and how they were going to lay out each option from a zone to zone perspective. They were evaluating architecture, what the architect actually wanted to see, evaluating the actual heating and cooling load and whether the zone was internal or external, how many occupants and how variable it was, what the square footage was, and then how loud the space was going to be as well. And so I'd kind of given my own recommendations, and I want to review those and talk through with the group why I made those recommendations and also get some feedback from the room as to what I might have suggested. So starting with the larger external zones. So this is actually facade on the south side and on the north side. So these are both external zones that we can see on screen here. And these are larger zones with higher heating and cooling loads. In this case, they also were very variable occupied. So these are open office environments. We can see, we kind of have these groupings of 6 or 4 tables or desks spread out throughout the square footage here. And generally these spaces, because they were so large and so open, could have higher airflows and still manage lower acoustics. So can anyone tell me in the room, if you were going to suggest a chilled beam or the fan-powered terminal in this case, which way would you lean? Yeah, so the fan-powered box, and there's good rationale for that. So the fan-powered box in particular is really great for the variable load nature of this zone. I think that's a big benefit. The turn down of a fan-powered box is a little bit larger than the turn down of a chilled beam, whereas a chilled beam, is much quieter. I think that's often a trade-off I think of. So that could be an approach, and that was actually what I recommended in this case as well. Now, the corridors are always interesting. They're frequently acoustically flexible. They're often determined by architectural design, especially if they connect to potentially like a larger atrium or lobby area. And this one, I'd be interested to know, does anyone have rationale for one or the other strongly? Fan-powered box or chilled beam, if we look at a corridor type space? What's your rationale for a chilled beam selection? Sure. So the rationale was it's a very transient space. It's not frequently occupied. The actual mixing of air is less critical, and the chilled beam could work better because of that. I think there's some great rationale there. Any thought process for why we'd maybe go the other direction? So you could potentially argue we could treat it as a bit of a VE opportunity, cheaper. Jason in the chat, thank you. We're on the same wavelength there. And that's because we could get one big piece of equipment with a lot of ductwork that could potentially be operating at a higher acoustical set point. And since it's a corridor, we could just serve a lot of it and really consolidate equipment. That's rationale potentially. Now, I would say this is kind of a toss-up. And I kind of said to the engineer at the time, go either way. It kind of depends on what you'd like. I would defer to the architect in this particular vision for the building, especially with Google. The architect tends to drive the project, so that was a consideration of it too. And then finally, these internal zones. So internal zones having smaller cooling loads, definitely much smaller heating loads, and also them being kind of grouped together because they're smaller, they need quieter operation. We have phone rooms with even 2 occupants or 1 occupant. We have meeting rooms. What would we suggest for these internal zones? Chilled beams, fan-powered boxes. Yeah, I suggested chilled beams as well. In particular, acoustics, I thought was a big driver for this. And when we look at a really small phone room, no single fan powered box is going to serve that zone by itself. So you're going to start to gang your zones together. So you're going to have 2 adjacent zones served by 1 VAV box probably instead, because some of these were as small as, 40 square feet, 20 square feet. They were tiny. And based off of that, even the smallest fan powered boxes may be too big. If we have chilled beams, they could all tie back to a thermostat. You could have individualized comfort control because we can actually size the chilled beam in particular for the square footage. I think that's a really nice asset, especially when cost is less prohibited by a company like Google. Anyways, I suggested chilled beams, and they did exactly the opposite of what I told them to do. So I said chilled beams in internal zones. I said probably chilled beams driven by the architect in the corridors. I said fan-powered boxes on the external zones. They didn't do any of that. They did the exact opposite of that. And the good news is the building is up and running. It's working exceptionally well. Everyone's comfortable. And yeah, the rationale for it, and that's a good question. The question was, why did they go that direction? And it came down to one singular thing. The owner and the architect liked the look of chilled beams lining over the desks. Completely visual decision. So similarly, this is an example where, maybe we use the wrong size Phillips head screwdriver by my estimation, but both worked for the job. And we see projects like this that would be fully laid out chilled beams. And we see projects like this that would be fully laid out fan-powered terminals. So of course, both work. There's rationale for either, but the great thing to know is it's just 2 tools in the tool belt. But if you choose either, you're not any further behind. It's just a different approach. So that's the project there, Google Block 38. That is in downtown Bellevue, which is, part of Seattle. It's a suburb of it. It's a beautiful building. And yeah, it's working great. It's commissioned now. Any questions on that? Okay. We're going to keep running here. And we're moving on to terminals and chilled beams in series. So this is a pivot. This is more of a discussion of we have a chilled beam system. We're utilizing series upstream terminals, so like a VAV box. What do we need to do to optimize this kind of relationship here? And so this is a little bit more theoretical. I want to talk about how the products work briefly. I said no more math, and then I have Bernoulli's equation on screen. Shoot me, I'm sorry. But I want to first talk about pressure and the theoretical approach to how we measure and control air with a beam versus how we measure and control air with a terminal. And so when we look at a terminal in particular, all of the pressures for airflow measurement and control and the way they work, like every other HVAC product, but in particular, the terminal is a nice depiction of it. It comes down to Bernoulli's equation. So the rationale that we're going to have a constant pressure, irrespective of if it's dynamic or if it's static. So whether it's, pressure associated with the movement of fluid or pressure that's associated with a static fluid in a container, we're going to keep some consistency, assuming that it's not a compressible fluid, assuming that flow is steady, assuming there's no negligible viscous forces. So the rationale here is an inlet grill condensing, through a smaller piece of ductwork means we're going to have a static pressure drop and an increase in velocity pressure. A fan is going to both increase the dynamic pressure of the system. So we're going to have that air moving faster. And then we're also going to have an increase in static pressure. And so the thought process here is at the end of the day, all things must be equal if we're looking at Bernoulli's principle in kind of an idealistic way. And that's kind of the way and the approach that we actually look at measuring airflow with terminals. So when we look at terminals, It starts with static pressure. Static pressure is what we're using for all of our duct design. So we're looking at static pressure drop across appurtenances within the duct, static pressure drop across the terminal unit. And when we look at these kinds of terminals, the main pressures we look at are the inlet static pressure, which is the not a pressure drop, but the physical pressure we would measure at the inlet of the terminal unit, which tells us how much energy we have in the system to get the air delivered and mixed into the zone. We have our downstream static pressure drop, which is in red on screen here. So that is the theoretical static pressure drop of the ducted system from discharge to diffuser downstream of the terminal unit. And then we have the minimum operating pressure drop, which is the static pressure drop of the terminal at its rated airflow, assuming the damper is fully open. So that's the terminal that would be furthest away from the air handler. Therefore, we're not throttling the damper at all. It's the critical path, the longest run of duct in the system. Therefore, the damper is in a fully open position. Now, when we look at velocity pressure, that's what we're using to actually measure and control airflow. And so our crossflow sensor, the one from Price, is called the SP300 crossflow sensor. Very critically, a crossflow sensor adds a lot of value to projects because it's going to allow us to have a kind of uniform duct sampling of pressure throughout the duct, which means if we have flex duct or if we have an elbow, we're going to have less kind of weight and influence to localize velocity, so better airflow measurement and control. And what this sensor is actually doing is it's measuring total pressure, or the summation of velocity pressure and static pressure. It's measuring static pressure only from some ports that are very intelligently hidden on the back of the SP300 sensor. I say that both because I am a fan of Price, but also it was way before my time. So whoever came up with the SP300 sensor is no longer at Price because it was developed a long time ago. But they hide those static pressure ports in a very precarious position. That really means you can never get any kind of velocity pressure influence from it at all, which makes for a really robust signal. And we take the difference of those, and that's actually how we measure and control for airflow. So when we look at airflow balancing for a terminal, we're really trying to look at two different points of airflow measurement and bring them together. We're trying to have a pitot traverse upstream in the ductwork, which is based off of velocity measurements that we're going to take through the ductwork, velocity pressure measurements. We're going to look at the K-factor cross-flow sensor measurement, and we're going to adjust this K-factor to essentially rectify any differences we have between these two equations. They should be perfect if we have a perfect ideal inlet and if we're at standard air conditions, but I don't think those two things have ever actually happened at the same time on almost any job site. We're always a little hotter, a little colder, higher or lower pressure. We're going to have duct system effect and ducted conditions that are going to influence the way that we're measuring and controlling airflow due to localized velocity. So what we want to do is to align CFM1 and CFM2 within a certain specified acceptable accuracy by adjusting that K value, generally plus or minus 5%. Any questions on terminal testing and balancing? How are we doing for questions online, Lindsay? We're good? Great. Okay. Now, when we compare this to airside commissioning and airflow measurement and control in a chilled beam, the reality is a chilled beam is not measuring, nor is it controlling airflow, right? It is a downstream endpoint to the ducted system. We need to balance the system to make sure that we get the right pressure in the back pan of the beam, so we have the right airflow delivery out of the discharge of the beam as well. And the way that we do this is by essentially getting a specific static pressure within the back pan of this beam. And there's a few things that means. One is we can't throw a flow hood in front of a beam and get an accurate measurement. Now, there's multiple reasons for that. One is it's going to add static pressure to the beam. And through adding static pressure, we're going to throw off the reading. However, more importantly, most beams, especially like a 2-foot wide active chilled beam that's 24 inches wide like we're seeing here, it's bidirectional. And the beam's not able to actually grab that airflow properly, and we're not going to like get a measurement this way and a measurement that way and know that it's accurate. So chilled beams are not tested nor balanced by utilizing a flow hood. And similarly, using an upstream pitot traverse doesn't necessarily guarantee that a beam is properly balanced, and that's true throughout industry, irrespective of manufacturer. We trust the beam's equation. We trust the static pressure in the back pan is going to lead to the airflow delivery rate that we expect. And that's true in industry, irrespective of market, irrespective of manufacturer. So what we would actually end up doing, yep. So there's a couple different approaches. One approach would be a constant volume system, where we would balance the primary air to deliver the ventilation rate for the zone, and we would maintain it. That's less common. Probably what's more common would be to have some form of demand-controlled ventilation, where we're going to be measuring carbon dioxide in the space and spanning from minimum to maximum primary air. Yes, but we can take each beam and duct them back to a single terminal. So we could have 4 beams to a terminal. And so that would allow for measurement and control of all of the beams serving the same zone with one terminal. Ideally, what we would do is have one VAV terminal per zone. With really large zones, that might not be possible. For instance, a zone that would require, 650 CFM of ventilation, like a really large zone, we would probably split that zone in two and have 2 terminals serving however many endpoint beams we need to properly mix and condition the space. Yes. So we can control the volume of outdoor air depending on the number of occupants in each room. The main way we would do that is through demand controlled ventilation. So measuring carbon dioxide, and you can do calculations that would assume a fully occupied space has a certain concentration of carbon dioxide versus a minimally occupied space has a different concentration. You'd measure that concentration and have the system respond based off of how much carbon dioxide is present. I actually, so the state of California, new construction, anything commercial, demand control ventilation is mandatory in every zone. So it depends on the market, but California new construction, there's a lot more hurdles to jump through, but Title 24, which is the energy code for the state of California, the newest version mandates it. So it is very feasible. It's definitely not as easy as just allowing your air to vary based off of temperature within the space. But yes, we absolutely can measure and control for occupancy. Another example of a different approach would be infrared sensors, like a Nest Home thermostat. So your Nest Home thermostat varies based off of occupancy. If you have a Nest Home thermostat at home, if you walk into a space, it senses that you're home, it changes the design set point of your home, whether you're there or not. And that's an efficiency improver. So we can get infrared sensors into commercial buildings as well, and they work in the same way. Another one which can be done as well, which I actually talk a little bit about in my next presentation, is badge counting and badge tracking. Now that's for like a large scale campus style of project, but I do know Amazon HQ2 does sequencing with badge tracking, so they know where their employees are all the time, which is kind of creepy. But it works really well from a sequencing perspective. So the question was, can we use DCV with chilled beams, or does it kill the induction rate when we get too low at nozzles? And we absolutely can use demand control ventilation with a beam. We just have to be cognizant of what our design turn down ratio actually is going to be. Similar with a beam as we look at with like a square plaque diffuser. You can get to a point where you dump and it's not effectively mixing in the space, and we're not getting induction in the case of a beam, or we're not getting proper mixing out of a square plaque diffuser. It's the same scope and discussion, whether we're using air outlets as an endpoint or we're using beams. We need to be cognizant of what the turn down capabilities are of the product. And sometimes that can be application specific or product specific. So the best thing to do at that point, if we're looking at demand control ventilation and maximum turn down ratios, would be to reach out to the manufacturer. In this case, Chris and Matt would have good metrics on that. I know often 3-to-1 turn down ratio would be pretty comfortable for a beam. Yeah. So the response as well from the product expert, Matt Boombla there, uh, he said we'd want to select the beam at the higher end of the pressure range. Sorry, I'm repeating this, everyone in the room, for everyone online. But we'd want to be higher to the point end, 0.5 to 0.8 of static pressure in the back pan of the beam, which would allow at least 50% turn down. But we'd want to have higher design day pressures rather than lower design day pressures to have more turn down. So looking at the way we actually commission these really quickly, we measure the static pressure in the beam's plenum via the port in the beam. We adjust the upstream balancing damper to match the actual pressure that we need. So that could be the price project schedule, which would come from the beam calculator, which Chris is going to look at for us shortly. Or that could be a static pressure off of engineering documentation as well, or out of the IOM, which is what I have on screen here. And ideally also, and this is just another point, that balancing damper, we generally want it for trimming only, so we don't want it to ramp really low down, mostly because of acoustics. And we want that further away from the beam if possible for acoustical considerations as well. So how do we do these two things in series? How do we rectify a VAV terminal and a chilled beam at the same time? There's a few different thoughts to this. I'm going to run through a couple of them quickly. So the first thing is we are still going to measure the static pressure in the beam's plenum via the port on the beam, and that's going to be the main way that we're measuring, testing, and balancing airflow. That at the end of the day is what we're trying to truly balance and control. Now, if we're looking at one beam serving or one terminal serving one beam, we would use the terminal damper as essentially the static pressure balancer for the system. So we would set the terminal's damper to meet the beam's design static pressure. Now the third step here, once we have the beam's pressure balanced correctly, is we would actually check the K factor of the upstream terminal, and we would adjust it to rectify the differences between the beam equation and the terminal K factor equation, which is going to account for ducted system effect, a lack of standard conditions. It's going to help to essentially make sure we're actually controlling to the intended max of the beam down to then the intended minimum of the beam. Now, a couple other points here, and I'll talk on these in a couple more slides, so I'll be brief with them. But if multiple beams are served by one terminal, ideally some level of duct symmetry is an asset. So rather than having a terminal with a super close beam, a medium beam, and a super far beam, if it's possible to do our duct work to kind of have it split like a trident almost, we're going to find that those three beams are easier to balance with one another just because the duct pressure drop is similar. So we don't need as much influence from a balancing damper, which is a really nice benefit. Then the other thing I'd note too, if duct geometry requires additional balancing dampers, which it often will with this type of system, one VAV serving a zone, two chilled beams, one's a little bit further, we're going to need a balancing damper on the closer one. An initial traverse at the terminal is sometimes done just so we can get the airflow close to set point to help with the balancing process downstream. It's going to make that process a lot more simplified and faster to have a good initial checkpoint for our total design airflow rate to the zone. So a quick example of this, and once again, pretty technical, my apologies, but let's say we have 360 CFM of fresh air required for a zone. Well, in this case, the way I've broken this out is 120 CFM through 3 individual 10-foot 604 size chilled beams. And that would result for 120 CFM for that beam type, we're needing 0.55 inches of static pressure in the backpan of the beam. And that's kind of ideal for that 0.4 to 0.6 range, which we're ideally targeting for design day. And with that 360 CFM as well, we're looking at a size 6-inch terminal. So that's just less than about 1,800 feet per minute through the inlet at design day for the terminal, which is a really good rule of thumb. If we look at the HRI certified ratings points, I know these are a little small on screen, but ASHRAE would say a size 6 terminal should be selected up to 400 CFM. Once you exceed 400 CFM, you should also upsize the terminal inlet once again to reduce generated noise and pressure drop. And so when we look then at the calibration curves for a 6-inch single duct box, what we're going to see is 120 CFM, which I've kind of carved out on the screen here. We're looking at 0.6 inches of velocity pressure for that terminal unit as well. And that's 360, sorry. So these graphs are always confusing to read when we move from the x-axis to the right. Essentially, we're looking at a parabolic curve that's created and graphed linearly here, which is why it's kind of interesting to read. Takes me like at least 30 seconds to pick out points on this every time I look at it. I don't know why my brain hasn't figured it out yet, but so what we have here is 100 CFM, 200 CFM, 300 CFM, and then about 360. So what would be the order of operations for this system in particular? Well, I would first initially balance the terminal unit using the standard K factor to about 360 CFM. I would then balance the furthest beam by modifying the terminal unit damper position with all other manual dampers fully open for the system. So I don't want those closed off because they're going to create undue static pressure. We're then going to trim the other beams with the manual balancing dampers. And finally, we'll adjust the terminal unit K factor to match the calculated chilled beam design day ventilation airflow rate. This is true if there's more. If you got a bunch of beams, eventually you'd probably need to use something like a Chicago method balancing procedure where you balance like one, then the second, then the third, then the second, then the third, then the fourth, then you bounce around. Sounds terrible. I'm glad I don't work in testing and balancing. Other considerations that are really critical is the terminal inlet should be sized to approach but not exceed that 2,000 feet per minute. And we should try to have 3 equivalent duct diameters. That would be an asset upstream of the terminal, especially in a chilled beam system. I think it's even more critical. And we also need to consider duct leakage, and steps should be taken to minimize it, such as sealing terminal slip and dries if we have a reheat valve or a silencer or a reheat coil, pardon me. And generally the rule of thumb here would be SMACNA Class B up to 2 inches of water gauge should be tested before balancing to make sure that we don't have too much duct leakage. That's a great thing to specify if you're using these products in series with one another. Of course, there's other options like low leakage terminals do exist. However, there's a cost add associated with them, and you're probably having to seal the ductwork downstream and still test the system anyways. So it might be more ideal to seal it in the same method that you'd seal the ductwork.